All right, ready to dive into some seriously fascinating research.
Definitely. Always up for a good brain teaser.
Well, get ready because this one's all about brain-computer interfaces, BCIs.
Ah, BCIs, the stuff of sci-fi dreams. And, increasingly, reality.
Exactly. And this paper we're looking at takes it a step further. It's all about decoding those complex EEG signals, the electrical activity in our brains to actually control stuff, turn thoughts into actions.
Now, that's where it gets really interesting. We're talking about helping people with physical disabilities, right? Giving them new ways to interact with the world.
You got it. The paper specifically mentions extracorporeal robotic devices.
Oh, yeah, I saw that. Sounds a bit like a cyborg movie, doesn't it?
A little bit. But this research is the real deal. So what kind of real-world applications are we talking about here?
Well, think about someone with limited mobility. This tech could help them control a robotic arm just by thinking about it. Or imagine someone who's lost the ability to speak. BCIs could give them a voice again, allow them to communicate, write emails, all through their thoughts.
That would be incredible.
It really would. And there's even more. Environmental control. Think adjusting the lights or temperature in your home just with your mind. The
Now,
possibilities are pretty vast.
mind-blowing stuff. But okay, let's get real for a second. The paper also talks about how tricky it is to actually decode those EEG signals. It's not like we've suddenly become mind readers, right?
Right. It's definitely not mind reading.
Yeah.
Not yet, at least. It's super challenging.
How so?
Well, EEG signals, they're notoriously noisy. Think of it like trying to have a conversation in a crowded room with music blaring, people talking over each other.
Yeah, I could barely hear myself think in that scenario.
Exactly. And that's what researchers are up against. Plus, these signals, they're not static. They're constantly changing, fluctuating. It's a complex puzzle to solve.
So no telepathy just yet.
Yeah.
But this paper, it does propose a new method to try to cut through that noise, right? Something called Anchored-STFT.
Yep. Anchored-STFT. And it's a pretty cool approach. Imagine you're trying to take a picture of something that's both really close and really far away.
Okay, I'm picturing it.
You might need to adjust your camera lens, right? Use different zoom levels to get everything in focus. Anchored-STFT does something similar. It uses different sized windows to analyze the EEG signal and the frequency domain, giving a much clearer picture.
Ah, so it's like having multiple lenses to look at those brain waves, getting a sharper image from different angles. The paper mentions something about this leading to a better trade-off between temporal and spectral resolution.
Right, it is. Basically, it's about getting more detail in both time and frequency. Imagine trying to understand a song.
I love a good analogy.
You need to hear each individual note, but also how they flow together over time, right? Anchored-STFT helps us capture both those elements, which is crucial for accurate decoding.
Okay, I'm starting to see how this could be a game changer. But there's more to it than just getting a clearer picture, right? This paper also delves into some pretty intense AI training techniques, like this GNAA thing. What's that all about?
GNAA, yeah, that stands for Gradient Norm Adversarial Augmentation. It's a way to make those deep learning models, the AI, even smarter. Think of it like training for a big competition.
Training montage time.
Exactly.
Yeah.
To really excel, you need to push yourself, challenge yourself, right? Spar with tougher opponents. That's kind of what GNAA does for the AI. It introduces these slightly modified inputs, almost like little curve balls during training.
To make it stronger, more adaptable.
Precisely. Forces the model to learn more robustly and avoid making those silly mistakes that less trained AIs might make.
So it's like giving the AI a crash course in all the ways EEG signals can be tricky.
Yep, exactly. And what's really cool is that these little curveballs, they're not just random, they're carefully chosen to target the model's weaknesses.
Ah, so it's like a personalized training program tailored to each AI-specific needs.
You got it. Push it to learn and adapt in a really targeted way.
Pretty impressive stuff. But all this training, it needs a powerful engine to run on right. And that's where SkipNet comes in.
Ah, SkipNet. It's all about efficiency. Think of it like a high-performance sports car. Powerful, but also lightweight and agile.
I like where this is going.
It's a specific type of neural network, a CNN, but with a slimmed-down architecture. This is key for real-time BCI applications where speed is everything. You don't want any lag or delay.
Especially if you're trying to control something in real time, like a prosthetic limb.
Exactly. SkipNet helps ensure smooth, seamless control by minimizing the computational heavy lifting.
Okay, let me see if I have this straight. We've got Anchored-STFT giving us a clearer picture of those brain waves. GNAA is training our AI like a champion athlete. and SkipNet is keeping everything running smoothly and efficiently.
You got it. It's a pretty powerful combination.
It really is. But this isn't just theoretical, right? They actually put this whole pipeline to the test.
Oh, yeah, they did. And the results are pretty exciting. They ran it on some real-world data using these standardized benchmark data sets to see how it stacks up against other leading algorithms.
So this is where the rubber meets the road, right?
Let's just say they weren't disappointed. They actually outperformed the competition across the board.
Wow, that's impressive. So they beat out other algorithms.
Yeah, they saw higher accuracy, better generalization. It's a pretty big deal.
Okay, but back up a sec. You mentioned benchmark data sets. What are those exactly?
Good question. It's all about making sure the tech can handle real-world scenarios,
Right, not just some idealized lab setting.
Exactly. These data sets, they're collections of EEG data from previous BCI experiments, kind of like standardized tests.
So it's not just cherry-picking data to make their method look good. It's a level playing field.
Precisely. And they used a few different ones to cover a range of situations. One of them was the BCI Competition 4V Dataset 2B. That's a classic one for testing motor imagery.
Motor imagery. What's that?
It's like, imagine doing a push-up, but only in your mind.
Mental push-ups.
Yeah, pretty much. The BCI tries to pick up on those brain signals, even though there's no actual movement.
Okay, I see. So how did their pipeline do on this mental workout?
It aced it. Not only did they achieve the highest average accuracy, but they also scored really well on something called kappa values. Think of it like this. It measures how well the classifier, the AI, can generalize beyond the data it was trained on.
So it's not just good at recognizing patterns it's seen before, but it can also handle new, unseen data.
Exactly. And that's super important for a real-world BCI. You want a system that can adapt to different users, different situations.
Makes sense. So one data set down, one win for the new pipeline. What else did they test it on?
Well, next up was BCI Competition 4V Dataset 2A. This one's a bit trickier.
Oh, how so?
This dataset involves 4 classes of imagined movement, left hand, right hand, feet, and get this tongue.
Wait, tongue movements, like sticking your tongue out.
Yeah. It might sound strange, but it's a surprisingly effective control signal, especially for people who can't move their limbs.
Wow, I had no idea.
Yeah. It's pretty amazing what our brains can do. But anyway, back to the experiment. Their pipeline did really well on this one, too.
Even with the tongue movements.
Yep. They outperformed several established algorithms, including some that are much more complex. It's clear their approach is bringing something new to the table.
2 for 2. They're on a roll. Any other tests?
They had one more up their sleeve, a real classic. BCI Competition 2 Dataset 3.
What's so special about this one?
It's kind of like the veteran BCI dataset, the one all the new algorithms have to measure up to.
The gold standard, huh? So how did they do?
They smashed it.
Yeah.
Not only did they beat the original competition winner, they also outperformed several other deep learning methods, some of which are way more complicated.
3 for 3. That's a pretty convincing track record. But I'm guessing it wasn't just a matter of running these algorithms and seeing what happens.
Yeah. Oh, no, there's a lot more to it than that. They went through a whole tuning process to optimize everything.
Tuning. What does that mean in this context?
It's like fine-tuning a race car engine. You need to adjust all the little parameters to get peak performance.
Ah, so they were tweaking the knobs and dials of their algorithms to squeeze out every bit of accuracy.
Exactly. For Anchored-STFT, they experimented with the number of windows, their lengths, how much they overlapped, all sorts of stuff.
So it's kind of an art as well as a science.
Definitely. And for SkipNet, they fine-tuned things like the learning rate and regularization techniques. It's a lot of trial and error, analysis, and refinement.
So they weren't just building a system. They were crafting it, perfecting it.
Yeah, I think that's a good way to put it. They really went the extra mile to make it shine. But there's something else in this paper that I found really fascinating. Their exploration of adversarial examples.
Oh, yeah, we talked about that earlier. It's like they're training their AI to fight off these little attacks that could throw it off course. But why is that so important for BCIs? It's not like someone's going to hack into my brain, right?
Yeah, maybe not hack into your brain directly, but
Yeah.
as BCIs become more commonplace, more integrated into our lives, security becomes a bigger issue.
Okay, I see your point.
Yeah.
What if someone could intentionally mess with a BCI? Like if it was controlling the self-driving car or a medical device, that could be really dangerous.
Exactly. And that's what makes this research so important. It shows that by incorporating these adversarial examples into the training process, you can actually make the system more robust.
So it's not just about making BCIs work better. It's about making them safer, too.
Exactly. And that's crucial if we want this technology to be truly reliable and trustworthy.
It's pretty amazing to think about, all this complex tech, all these algorithms. But at the end of the day, it's about what this research actually means for people.
Yeah, absolutely. It's about the real world impact, how this tech can change lives.
Exactly. Yeah. And on a practical level, this research seems like a huge step towards making BCIs, more effective, more reliable. Are we getting closer to seeing things like thought-controlled prosthetics becoming a reality?
Oh, absolutely. We're moving in that direction. Imagine someone who's lost a limb being able to regain dexterity and control, all with a prosthetic that responds seamlessly to their thoughts.
That's powerful stuff.
It is. And it's not just about restoring lost function. Think about the potential in other areas, gaming, education, even art.
Whoa, yeah. Could we one day control virtual avatars with our minds? Or learn new skills through direct brain stimulation?
The possibilities are pretty mind-blowing. Create music just by imagining it, explore virtual worlds. But of course, with any powerful tech, there are those ethical questions we need to think about.
Yeah, we've touched on that a bit, privacy for sure. If we're decoding thoughts with this level of accuracy, how do we keep those thoughts private and secure?
It's a huge concern. We need really solid safeguards to prevent unauthorized access to people's brain data. Make sure BCI tech is used ethically responsibly.
Absolutely. And then there's the whole issue of access. BCIs right now, they're still pretty expensive, require specialized knowledge. How do we ensure this tech benefits everyone, not just a select few?
You're right. Accessibility is key. We need to be working towards a future where BCIs are affordable, user-friendly, and available to anyone who could benefit from them, no matter their background or where they live.
It's been such an inspiring deep dive, but it's definitely given us all a lot to think about. Technology is only as good as the intentions behind it, right?
Couldn't have said it better myself. As we keep pushing the boundaries of BCI tech, we need to keep those ethical considerations front and center. Make sure it's used for good.
Well, listeners, we've reached the end of our journey into the world of brain-computer interfaces. We've explored some pretty complex algorithms, imagined some incredible possibilities, and wrestled with some big ethical questions.
It's been a real adventure exploring this cutting-edge research. Hopefully you've come away with a better understanding of just how powerful and how potentially transformative BCIs can be.
If you're buzzing with questions or thoughts after this deep dive, please share them with us in the comments. We'd love to hear from you.
And if you're eager to learn more, we've got links to the research paper and other resources in the show notes.
Until next time, keep those minds curious, stay engaged with the world, and remember, the future is ours to shape.
It is. And with smart innovation, a commitment to ethical development, the possibilities for BCIs, heck, for humanity, they're pretty much limitless.
And that's a wrap for this episode of The Deep Dive. Thanks for joining us on this exploration. Until next time, keep those brains buzzing.